It's going to be a powerhouse of wisdom featuring interviews. Why do you think mechanical engineering hasn't really, gained or gathered so much of attention as compared to computers at the
Yeah.
moment? Because it could be a computer era, whatever.
Yes.
However, whatever you're explaining to me right now,
Yeah.
it's so interesting in terms of fatigue calculation or
Yes.
in terms of RPM and
Yes.
the car crashes
Yes.
or the potholes, and which is
Yes.
very day to day daily
Yes.
routine that we go through,
Yes. Yes.
and that's something very tangible that you can actually make a product out
Yes.
of, right?
Yes.
So why hasn't it yet garnered so much of attention, and I would say a celebrity kind of a status? Because I feel this should have been, but
Yes.
it did not.
Yes.
um
Yeah. It's a very nice question and very close to my heart. I'll tell you, whoever comes to me who has done that 12th, and if suppose ask me that I have these many likings, I don't mind doing mechanical, but actually I want to do computers, and I'm not able to get into that. So what should I do now? So to all those students, I keep telling them, please pursue one core mechanical engineering, one core engineering subject. It could be mechanical, electrical, electronics, civil, or metallurgy. These are the core subjects. Out of that, mechanical, electrical, electronics, and civil are really, really core subjects. So, in my opinion, now this celebrity status to computers has come because anything that is new catches your eyes. So, in the computer engineering, you are many of the times people become software developers. And I will tell you, lot of people, lot of engineers, mechanical engineers that I know of have done their BTech, have done their MTech, and finally landed up in the computer software. They are into their working. The working area is computer software, but at back end they have done BTech mechanical, sometimes MTech mechanical also. Jokingly, I call this as a brain drain from the core subject. There are brain drain from my country to the USA. Okay, acceptable. Why? Because these people learn something there and come back. But the brain drain from core engineering subjects to these subjects, according to me, I am not saying that it is not to be done. Many a times when mechanical engineers develop a software for some engineering structural analysis, they are better off. Why? Because they have understood the mechanical engineering at the back end. And now they are developing some software in this engineering structural area. Yes, they will do excellent. They will do excellent job. But those people who directly get into computers, I have a feeling that the basic engineering knowledge which one has to have, which will mature you towards any further thing, is a necessity. I don't want to say this, but see, computer software is a white collar job, software making. Now, when I learned mechanical, I had to go to workshop. I did all those smithy experiments. I did carpentry myself, and I enjoyed doing it. Even today, many a times when I have to sort out a problem, I have to go to workshop and make my hands black. I have to stand there for some time and learn from production workers what exactly are things are happening there. I think the white collar jobs have got a lot of prestige these days. So the celebrity status could be only due to that. But as you said, and there are some interesting softwares also being developed. I'm not at all denying it. All those necessary things are happening, even in the commercial area. Even in the commercial area like Amazon, you are buying things sitting at your home, and something reaches to me right from US or right from my own country, from Kerala, whatever. Why I can buy? This has become possible because a lot of people have worked on software. A lot of people have made it possible. So I am not at all denying that. I am only saying that somebody, if you know that you like a core engineering subject, you should not feel shy about it. At least you pursue that. It will give you results.
Right. Another thing that comes to my mind is, since you said that you've actually put your hands in the carpentry of the projects
Yes.
that you might be
Yes.
working and stuff,
Yeah.
but what was the percentage of boys versus girls, and what is it right now? I think it's still the same. I would say not many girls,
Hmm.
women population are into mechanical engineering, and the
Hmm.
one thing that comes to our minds, to any
Yeah.
common man, when it comes to mechanical engineers, is mechanics. And
Yes.
when it comes to mechanics, they all probably would be visualizing grease to the
Yeah, yeah.
hands,
Yes, yes. Yeah, yeah,
or I
very
don't
much.
know what, you know. So
Right.
white collar versus a blue collar
Yeah,
versus
yeah.
a some other
Yes, yes.
color,
Yeah.
and could be the reason why women population is less as compared to men. Is it really the case?
Nowadays, of course, during my time, yes, there were less number of girls. Now, my batch was very fortunate to have 9 girls in totally 110. But my earlier batch and my later batch, all of them had two, three like that. And I'm very proud to say that in what whoever was in my batch, my friends, 9 girls, all of them are working today, and all of them have proven their mettle as mechanical engineers. So I'm really very happy to share this with you. These days, lot of girls are doing, I mean, better percentage than that time. There are some reservations also for girl students. So lot of girls are coming into this stream, but many of them don't remain in mechanical. As you know, they shift to software, they shift to this, that. Now coming back to why, all these workshop related things, why is there so much of phobia that why girls cannot do it? I'll tell you a little simple example. Since the childhood, at least at my time, now things have changed. But in my times, our mothers used to tell us to do a lot of housework, which required physical effort. We didn't have mixers. We had to do so many things with our own hands, applying force. It's not that, in fact, I would say that boys were not doing and we were doing. So, you know, I used to make chutney by using those ancient mechanisms. We didn't have mixer that time.
Stones.
Stones were there. We used to do it, both my sister and myself and my mother. And yes, but we didn't feel that, that. And when I went into the carpentry, when I went into the smithy, I didn't feel, that I'm not able to do something. So I don't know why such thoughts come to, and my parents never ever felt that how will my daughter do mechanical engineering, and why not so many people. They never told me to change my line. They said, we are sure you are strong, you will do it. That's so that gender inequality doesn't have to be there actually. I don't know why it is there in people's mind.
Another wrong notion that common men have is mechanics is equal to actually going ahead and only going, starting your own garage as a mechanic.
Huh.
So it's a very strong, wrong assumption.
Yes.
And through this platform of podcast, I would really want you to speak a little more and make more awareness, which is
Yes.
not the case, um,
Yes.
and educate the population more.
Exactly. Uh, you had, suggested towards one subject of computer software and people inclined towards computer engineering. I'll tell you, after doing my B, for some years I was involved into, I got an opportunity to work with a premier research institution working on automotives. So I got to see a lot of things. I got to see all state of art equipment there. And for few years I was into testing, and for later years there was a requirement of using a software called as finite element analysis. That is the subject. So what basically this subject is you there is a this is a computer aided engineering analysis. So there is a software which is made available to you, which is able to take the mathematical model inside. Now I'll explain a little about these mathematical models. See, you have a structure in place. That structure you must have seen, like when the buildings happen, when your flat is being constructed. Those drawings have come to you. In this is your room, this is your bedroom, and this is that. This is the same way. Structural models can also be made in the 3D. So nowadays there is a lot of 3D modeling tools available. So that is called as solid modeling stage. So all the mechanical structures can be made into solid models. Now those solid models are fed to this finite element analysis software. What this software does is it converts those solid model entities into mathematically understandable language. When I say that, it is converted into these finite elements, means each structure is made into a lot of small elements. Now those small elements are connected by something called as nodes. And to that mathematical model, you can apply the loading on computer. On computer, you are analyzing this. you are having a model of the real structure. You know what is the load on the real structure that you are applying. You know how the component is sitting in place in the real structure. You apply your boundary conditions like that. And now you have to do the analysis. What the analysis gives you is how the structure would deform. What are those stresses? Where it is going to fail? After how many hours it is going to fail? Okay, this is the information which is made available to you. So since year 89, I started working using this software. And whatever technical papers that you read out, most of the work is done by using simulation and validating it with the actual testing. So this has been my work area since 89. So I use that software. We calculate a lot of predictions, and we do a lot of structural predictions. And what happens is, you don't have to make multiple prototypes. You save time in doing so. Okay, this is the area which is where it is going to fail. For example, in the cars, we know that, okay, in this floor component, or in the chassis component, or in the suspension components, what are those locations where the structure might fail? We predict it beforehand. We can modify it. We can take multiple runs in the computer itself. And then the structure gets finalized. And that is the structure which finally gets manufactured. So your manufacturing trials are reducing by using these simulation techniques. So I am into simulation since 89. And this is a very interesting topic. So I will say that those students who want to pursue mechanical, but want to do something very advanced in terms of simulation, in terms of prediction. So this is a very good line. And nowadays there is a lot of demand to these subjects. When I started using it, I had to go to the industry and tell them, look, you will save time. This is the software we are having. In my institution, we had it, and very few industries had it that time. So I had to go all out to tell them, you describe them the technique, and to describe them that I am able to do it. So this was a twofold problem for me. Today, that is not the case. Today, the whole of the mechanical industry, automotive industry, aerospace industry, everybody is using day in and day out this software. The Chandrayan mission you have seen, and if you have heard the officer speaking there, they said we did a lot of simulation. So this is the simulation they did. They simulated so many things that they were 101% sure that yes, this is going to work. So simulation helps the manufacturer get 100% confidence in his structures. So I would suggest that this is a very good area for new brilliant engineers to get into. So
this is a very interesting conversation, getting into a lot of opening a Pandora's box of a lot of wisdom and a lot of knowledge and interesting aspects of mechanical engineering, not only on land, but also underwater, in the air, and into the solar system, because you just cited an example of Chandrayan stimulation. Since you have been doing a lot of stimulation studies around the cars especially, I'm sure mechanical engineering was 101% applied and is an important aspect of the Chandrayan mission as well. So to make this a little more interesting, and especially for the students to hear in more, because this is like a fresh cake from the oven right now, how the mechanical engineering was implemented and executed during the Chandrayan 3 mission.
Oh yeah, I'm sure, based on my knowledge of automotive, the way they must have analyzed this is just out of my imagination that I'm telling you. I have no direct knowledge about the team and how they work, but if I apply the analogy of our automotive engineering to that, for example, the vehicles, when we study when the vehicle prediction we do based on whatever road inputs are given, that is the time when we also have to measure how are the road inputs. I'll tell you, the suspension which is designed in Europe, for example, you know the McPherson strut, which is available on our cars. If you get the European design, this happened 20 years ago. People got that same strut right into India, and it was proven in European roads, but in India it broke in half a time, because we have to study our Indian road conditions. Now that is the reason why people had to make the road profile ready. So similar to that, we know that south pole of moon has a lot of undulations, and that is why they had a problem in Chandrayan 2 mission. In the Chandrayan 3 mission, they knew that the land surface of Chandra has a lot of undulations. Like our potholes, somebody also joked that they must have studied on Bangalore roads and probably designed the rovers. So jokes apart, but yes, we had to do the road profiling. 20 years ago, my institute had to take up a project for Indian road profile digitization. We took vehicles on Indian roads and we measured how are the village roads, how are the our express highways, how are our city roads. So what is the statistics? Then that statistics comes back, and vehicle design is on the other side. This road statistics on one side, and then when I do simulation, in my simulation, I have to use those conditions of roads and derive the roads which are coming on my suspension parts. Once those loads are derived, then I design the suspension very properly, which works in our conditions, our village roads. There are four-wheel drives. Four-wheel drive vehicles are available today. They go on very difficult terrains. Why they are able to do it is because a lot of predictive work has already happened. That on those roads, what is going to be the loads coming onto that? And that is all we predict. We do it using a lot of vibration theories, a lot of simulation analysis, a lot of things doing this finite element theory. And we predict that, no, in order to withstand to these conditions, the section modulus has to increase or the material has to change. The stronger material has to, come into picture. So this is how, these are all the techniques which usually all simulation community will apply. So same thing they must have done, is my judgment.
So would it be wise to say a combination of mechanical engineering and automobile engineering, or a combination of mechanical engineering and aeronautical engineering would be an awesome career for anybody who wants to make their career in the future?
Yes, absolutely. Absolutely correct. I would say if somebody is very fond of mechanical subjects, then it's a good idea to do BTech mechanical and MTech into aerospace, or maybe even MTech into computer science. Doesn't matter. Why I'm saying is MTech into computer science will be a good combination, because the person knows the basics of mechanical and now he is able to apply in any new software, hardware, electronics. See, all these our vehicles are full with electronics also. So things have, subjects have become so interdisciplinary. It's not that you study only one. See, for example, in my case, in 83, I was a simple mechanical engineer. But later, I studied so many things. I continuously kept on reading new things. This finite element is a very highly mathematical tool. So I had to also learn theoretical background of that analysis in order to apply it properly. If I don't know how mathematics is working in solving my problems, I don't have to create a software, but yes, I have to know what are the algorithms used to use it correctly and to use it to the best of its ability, so that whatever results I am creating have to really match with the reality. See, finally, rest of the pudding is in eating. Unless I match my simulation result with something happening on the test bench, it has no value at all. So continuously you have to do this. Fortunately, I had the opportunity to learn it in my institutional days. Even later, when I worked as my own, out of 40 years, 20 years are my institute days, and now 20 more years of my independent working now as a consultant. And I call myself as a consultant, but I have my own, I have my own setup, and I solve the problems of structural problems using the software that I was talking about, which is called as ANSYS. So I'm having all that set up in my office, and then I'm giving solutions. So that's how.